So the good news, this has never happened before when I was presenting Julia at the OpenGeoHub summer school, right? I was always happy if someone came in, but. So for next year, we should get a bigger room. Okay. Let me know if I can actually start. And oh, okay. Everything is recording and live. Crazy. Okay. Welcome. Thanks for joining me in such numbers. I'm Maarten Pronk, and I will be teaching, well, an introduction to Julia, then slowly moving to some more advanced Julia, and then after the break, we'll go in depth on some topics. I like to stand for this part, but I fear I have to be sitting down at the laptop sooner rather than later. So I'm Maarten. I work at Deltares, which is a Dutch research institute. And it's a non-profit research institute for water and subsoil. As you know, Netherlands is quite low, and we have quite a lot of water. And this needs to be managed, and we need to research these things. We need to build new storm flood barriers. All these kinds of problems, that's something we do at Deltares. And that's not just in software, and sometimes using Julia, but we also have large-scale facilities. I think we have the biggest wave flume in the world, where we basically generate waves and then crash them at dams that we build as a skill model, a one-on-one skill model. We have very much more cool research facilities. So a little bit about me. I once studied architecture.
Anyone suggesting me to join Google Meeting, I will do it.
Ah, that's a good one, actually. We should have put it on a notice sign on the door. Anyway, once I thought after high school, I thought I don't want to work with computers. All those people behind computer screens. I did that for my high school years already, so I will do architecture. The architecture faculty burned down that summer, and afterwards everyone was really working with computers. No drawing screens anymore because those were gone. I even started a master's in architecture, did not finish it. I switched to geomatics, so geoinformatics as you might know it. And that worked really well. I really liked it. And from there on, eventually, I started at Deltares, and that's been 10 years now. I feel quite old. And also 4 years ago, I started an external PhD program at Delft University, back with my old supervisor. And a little bit more about my research comes after the break. So I basically, during the day, I work at Deltares. Some part-time, I try to do a PhD. And then at night, I'm an open source developer doing more Julia, specifically geospatial Julia. So I wrote a geodata frames package, which is like GeoPandas, or I think SF in R. Geomorphometry, which I will talk about later, and the SpaceLighter is also related to my research. And this is the third time I've been giving a lecture on Julia here at the summer school. So hopefully you checked out the previous videos. Did you? No. That's why I'm here and actually giving this lecture. It's definitely sort of a repeat of the previous years, but we'll see how far we get. So I want to start with a short introduction and a quick demo, first 30 minutes, which should be really high level on Julia. And then I will try to go into each specific feature that I really like the package manager or some internals. That will take longer, but slightly more advanced. And then the last part of this session, I will dive into the geospatial stack, introducing some of the packages. Then we have a nice break. I will do 30 minutes of geomorphometry in Julia, maybe even shorter. And I will give the floor to Daniel here, who will teach us about discrete global grid systems in Julia. So we merged the original 2 separate sessions that were in the program because we basically saw the numbers. The introduction was very popular, and then basically it splits into both sessions. And I actually really like to follow Daniel's session, which was impossible in that way. So we merged it. So this is the merged schedule now. Well, I think that's it for that stuff. So how many of you already use Julia? Yay! Well done, Daniel. Thanks for that. Okay. Well, then it's good that we do an introduction. And I hope you guys can still follow along at the end of the session and also for the next packages. But yeah, then let's start. Sorry?
just attracted by the name.
It is a very attractive name, and it's. I think the developers left it unclear specifically who came up with the name, who was inspired by what. I mean, in maths, there's the Julia set. There's some mathematical structures that are called Julia, without it being a person at all. So who knows? Sometimes it's definitely confusing. I mean, searching for Python, I think maybe 30 years ago, beginning of the internet, you might result in snakes, right? Images of snakes. But if you type in Python now, you definitely get Python results. If you type in Julia in Google, not so much. That still happens sometimes to me. OK, a little bit of warning. I will not be trying to sell you Julia. Because one, well, I make no money out of Julia, so there's nothing really to sell. I don't have a way of making money with Julia, otherwise I would maybe do that. So if you're happy with using the programming language you're now, please continue to do so. Right? If you have a deadline that's slowly approaching, or you're finishing your master's or your PhD thesis, don't start a new language. Right? I mean, it's nice procrastination, but it will introduce a world of pain once you really need to finish something. I think I told someone at lunch that secretly, a few years back, I still did some of my plots for my papers in Python just because it was still slightly faster for me to do that, because it was less friction than doing that in Julia. Now I switched, by the way, but still. Then again, if you're maybe at the start of your PhD program, or actually have some free time, I really like to learn a new language, well, you've come to the right place. Let's do so. And this was also in response to Tom, because I think Tom in the opening session said, I'm here to convince everyone of Julia. I'm not. So Julia started at MIT. PhD students, computer scientists, well, not all of them actually. Young people, and they wanted to change the world. So what do young people do when they want to change the world? They write a manifesto, right? And they said, we're greedy, we want more. We want the language that's basically best at everything, right? As good as statistics, as R, maybe as easy to use as Python, maybe as good as linear algebra, as MATLAB, but as fast as C or Fortran or whatever you're using. They wanted it all. Well, normally that you don't succeed in that, but I think, especially now that we're many, many years later, I think they partially succeeded. So these are the original authors of the language. And it really started out as an MIT PhD research project. But currently, so many years later, we have a high-level, high-performance dynamic language for technical computing. And technical is basically, well, if you're at a technical university, or you probably know what technical is. Engineering, analysis, math. It's not really a generic language. I mean, you can do generic things with it, but if you want to write I know people who write web servers in Julia, so I don't want to insult anyone who does that, but I guess it's easier to go to Python for such things. It's only 13 years old at the moment, and version 1 was only released in 2018. So it's a really young language. And you'll notice that. I mean, it's a drawback, I'd say. Python being really, really popular right now, it's just as old as I am. I'm also from '91. And in the first 10 years of Python, no one had heard of it. I think in the 20 years after that, then it was becoming slightly popular, but still had huge problems. And now we're 30 years later, slightly more than 30 years, sadly, also for me. And it's really, really popular. And the ecosystem has taken off, and it's now the most popular programming language. So things take time. So everything that's not yet great with Julia, it might still get better. The language is open source. So it's out there on GitHub. You can go there. You can find a typo in the documentation. You can make a pull request, and you probably have contributed to the Julia language. I've done so, and many others, because we're at 1,500 contributors, and it's pretty popular. And the nice thing I like about Julia, because it's so young, it's a bit of cheating, I got to admit. You can basically look at all the other languages that have come before, right? And saying this language is bad at this, but very good at that. And you can just nick it. Or it's a slightly slower process than that. So Julia is like Python and R that has an interactive replicator. So, right, a command line where you can type in 1 + 1 and you get an answer back. It has built-in documentation. It has a built-in project manager, built-in tests and environments. And there is even a binary package manager, all built in Julia. I always like to point out to Python that the Python ecosystem in terms of package installations is still sort of unsolved, right? First, you have to install binary wheels. Then people went to Conda. Now Conda is evil. And then we went to Mini Conda. And now people are switching to UV and Pixie. All to basically, and then there's pip and pipx, and all ways of managing packages in Python. And in Julia, there's just a built-in package manager from the start. And that's what you can use. So why would we need a second language? And I think the problem is best explained as the two-language problem. And who has heard of such a problem, actually? Oh, one. Cool. Cool. Well, I normally say, normally you have, if you have a problem, you want to solve it, right? Or you have a great idea and you want to implement something. You start hacking away at your keyboard, and you probably produce really, really ugly code. It's not tested. But eventually, after loads of bugs and syntax errors, you get a first plot, or you prove that it works. So that's, let's say, prototyping. And normally you do that in a very quick and easy language, like Python, like MATLAB. And then comes the painful point that you need to scale it to the world, or you need to run it in production. And that simple script that hacks, they cannot scale. It doesn't work, right? And normally the solution is basically call your IT department and say, do you have a C++ software engineer for me? And they will take your code, laugh at you a little bit, and then implement it with software engineering standards nicely. But it's not your code anymore, right? Your solution has fled to this other code base. You don't understand it anymore. You cannot change it. So you get basically two groups of developers. And that your original idea is sort of dead. You cannot iterate easily on that. And you see this everywhere. All the nice packages you use in Python, and even in R, are probably packages that are actually written in C++ or Fortran or C. If you use NumPy in Python, that's actually Fortran, right? If you use GDAL, the GDAL bindings that you use in SF in an R, that's C++. GEOS, Proch, all those packages are C++. So if you have a bug in R or Python with those packages, if it's just in the interface in linking, you might be able to fix it in Python. But mostly the problem is actually in C++. And happily, there are developers who will help you with that, but you can probably not change it unless you learn that language. And Julia tries to be both, right? You can prototype in it, and then it will probably still be slow and a bit stupid. But if you optimize it slightly, maybe with the help of someone, you get it to the same speeds as C++ or Fortran. And then the code is still in Julia. You can still read it. You can still recognize your original idea in there, and you can iterate on that. I think that's the promise, and I've seen it working loads of times, and that's what I love about Julia. So yeah. Oh yeah, I had to put this in there. So is Christoph here? No, okay, you've seen him around. He was also on the panel, second panel on the left-hand side. Christoph works a lot in R and such, but a few years back he made a vector benchmark and raster benchmark GitHub repository, and he started benchmarking R and Python, right? They had an R and Python fight. And then some friends of mine, they also introduced Julia benchmarks to that. And Julia was way faster in most of these things, or at least equal. So we see that Julia can actually be fast and pretty nice to use. And the latter I hope to convince you during this lecture. So yeah, let's do a demo. I have to sit down now. So how many of you actually installed Julia? Oh, just good. Okay, that's most. And most of you are on Windows and use the Windows Store? Okay. Yeah. And maybe Jupyter Notebooks, but should work. I'm gonna drop into a terminal. If you don't know what the terminal is, please look at your neighbors. I think that's easiest. So I'm on Mac here, but this should one more guy on Mac. More people, yes. But you have a common prompt on Windows as well. And the nice thing about installing Julia on Windows from the Windows or Microsoft Store is that it also installs Julia up. So this is another ID that Julia has basically nicked from Rust, because it's almost the same code. You have Rust up, which is a Rust version manager, and Julia up is a Julia version manager. So you don't need to download a specific Julia version from its website. You probably now have Julia up installed, and you can test that by basically entering that command in a command prompt. And this manages your Julia installations. So I have several Julia versions installed, few older and the latest release version, which I'm using here, which is 1.11.6. Aren't we at 7? Well, I don't know. So this is good to have, and it's also easy to basically say Julia up at 1.10, and then it will try to download the latest 1.10 version. Of course, this is slow on my internet connection. It says already installed. So this is quite useful. No need to download new R versions, Python versions via external services. Built in. So then we can start Julia. And then you're dropped into, well, with a beautiful logo in Unicode and such, you're dropped into a replicator. So this is just like R and Python that you can drop in and do interactive things like the fantastically 1+1. So this is one mode of running Julia. Of course, the other one would be saying Julia and then run a script called the whole file. So basically everything that's in that script, it's executed. So we can, the install.gl should be in the GitHub repository. Oh my, I did not expect that it was updating all this stuff. Oh no, oh no, okay. Oh, made a typo here, that's nice. Okay, I'm gonna ignore this demo effect because of course everything will break now. Let's go back to Julia. I think there are a few nice built-in things in the Julia replicator environment here, is that you can enter specific keys and you go to a different mode. So this is now just Julia. So everything you enter here will be executed as Julia code. If you go to question mark, so type in question mark, this prompt switches to yellow, becomes a help question mark sign. And now if I type in a function like sign, you get the help mode for this function in Markdown. This is pretty useful, especially if you don't know the correct syntax or all the keyword arguments. And similarly, there's another mode that I want to introduce to you. That's the block brackets, so the square brackets. And then you drop into package mode. So in this mode, we can add a package. So this is the built-in package manager in Julia. If you followed in Mattermost the instructions, you basically already done this to some extent. Maybe not via this mode, but more interactively. I'm going to remove the geo package because I'm not sure what that, yeah, that's good. And if you are in this package mode, you can just hit backspace and you go back to the Julia prompt. So there's a built-in package manager. You can remove packages, update, all of that. Ideally, I don't do that here because I might either break the environment, or I think my internet is still using my phone because it's incredibly hot in my pocket. Yeah, this is still on the hotspot because I don't trust the Wi-Fi. But yeah, so getting new updates using the built-in package manager. I actually made some updates to the package we're using. Like I made a fix to geomorphometry, which I'm demoing after the break. So if you installed all the packages like beginning of the week, you should maybe update. Otherwise, you will see a few bugs. There's one more mode that I want to show you just from this, and that's the semicolon. And then you hit the shell mode. And then I'm basically back in my command prompt. I can do, I'm on Mac, so this would be a Linux command like ls. In Windows, you probably would do dir for all the files. See, this is all the files in this local folder. So from a Julia prompt, I can actually hack around my system pretty nicely, execute commands, check things. So I really like this. That said, I don't think you can develop big projects just hitting the Julia interactive mode. So let's exit it. I do that with Control D, but exit should also work. And I'm going to open Visual Studio Code in this folder. And this should be familiar to all of you. Oh, no. Using Karameki. So who has Visual Studio Code up and running? Oh, that's actually pretty good. Okay, I wonder what happens on the status bar right here down below. It says Julia environment. And I've chosen my checked out GitHub repository with my code base, and it has a certain project. And so I can actually use this package. I can open a new file. Wait, I will demo that actually. And save this as a GL file because the Julia extension is .gl. So now it actually recognizes that this is Julia. And if I then hit Shift-Enter on this line, VS Code will open a prompt. So it has an interactive session. It's starting now on the right-hand side. And next to my code, there will be a check mark that it actually executed this code. So this is a way of interactively executing code in VS Code, just like I just done it in the replicator, but now in VS Code. And I can do 1 + 1 again. And it will set 2 in this prompt here. Is this visible enough also from the back? Okay, no? Bit larger, even larger, oh my. Okay, I need to shuffle things around now. Yeah, I even need to click these breadcrumbs now to click Julia. So normally I'll make it slightly smaller. Yes. On the left-hand side, there's all these plugins that are enabled by VS Code. And the one with the triple circle, the Julia logo, if you click that, it will open a workspace, documentation, and a plot navigator. And I think now this interface in VS Code is familiar to you who are using maybe Spider for Python or the R editor, I forgot its name. RStudio, oh, that is quite straightforward, of course. In the sense that on the left-hand side in the workspace, I actually have my variables, I have the modules, and if I say A is 1, which is how I basically assign 1 to the variable A, then A is 1 appears in my workspace. And I can expect that if that's if that would be an array or vector. I can write functions in Julia. Oh, that's called a function, actually. I should have disabled my AI autocomplete, right? Then again, AI is actually useful, right? Especially if you don't know the syntax yet. So if you have a good AI, then it will probably autocomplete Julia functions correctly. But yeah, I can make a demo function that takes A as an argument, and okay, why not? It doubles A. And so you already see there is some specific syntax here. We need an end statement. And it comes from, I think, MATLAB as well, especially from Fortran. Some languages use, or Python uses basically indentation to figure out where code ends. And people say that's a horrible choice, but if you're used to it, it's fine. I also write Python code for my work, my daily work. So sometimes I get confused and write a double or a colon here, right? And then nothing works. So this is Julia, not Python. And if you say, we can also add a docstring. So this is how you write docstrings in Julia. As you can see, it's on top of the function, just above it, instead of inlined, which you might be used to. And of course, we can execute this also in the replicator by saying, by hitting Shift-Enter. And then we'll see in the workspace, there's now a demo function. And if we say right-click, show documentation, the documentation panel nicely says a demo function. And you can write markdown in this triple quoted string. So you can do cursive, you can put in images, you can put in code blocks. And of course, you can even write doc tests if needed. And, well, maybe one more thing before I go back to the presentation, and then we can do a deep dive. Yeah, it takes this from the AI is reading my other demo GL function. So in Julia, you can make ranges. So we can start at 0. Then we say colon. Then we take a step size of 0.1. And we do this until 2 pi. If you want to type pi, you can do backslash pi and then tab. And then it auto-completes into the Unicode icon. Of course, Unicode is valid Julia code, just as it is in Python. But it's very nice to use this, especially if you're writing or copying from a math paper or vice versa. So this becomes a range. And we can plot this range. And we can first call sign on this whole range. And then basically for each of the step size, I calculate the sign. And then we can plot that. And then we get a nice plot. And now also the plot shows up in the plot navigator. So I think this is everything I wanted to demo just in this very short part. You can do plotting, there's math, help functions. Yeah. So let's switch back to my presentation. So from these simple beginnings, you can actually build quite nice programs. I'm going to stand for this part again. Oh, way better. So you might ask, who introduced Julia and why am I using Julia? And that's because a colleague of mine, Martijn Visser, who also taught at I think the summer school of 2020 in Siegburg, he was working on a Python project, and he had a very large-scale Earth observation data set, trillions of points. He tried to process that using Python. It worked. I mean, it's what he was looking for. But the whole processing would take months. So he had a problem. Now, the right answer to his problem back then would have been actually to call C++ software engineer from Deltares. I think that would have been the right project choice to finish that project quickly, etc. But he didn't. Somehow, back in 2014, he was aware of Julia. What?
I don't know if it's the connection, but you're out of the call. You're not presenting anymore. I'm sorry.
Okay. The hotspot is still on, so. Okay, and am I back on the call? Okay, so after each half hour, I'm being kicked out of the call, or my Mac leaves voluntarily. Okay. Anyway, this wonderful colleague of mine, he somehow knew about Julia, a very young language back then, and he switched to that. And that was still, on his own, that was still not fast enough. And that's when he called me to say, do you want to work on this project? It had to do with elevation modeling, which was a bit of my thing already back then. So I helped further develop the Julia code and even parallelize it. And that's how Julia was introduced to Deltares and how I got in contact with Julia. And then, well, we did a few projects, nothing major. I think we had enough people to do some pizza courses in Deltares back in 2019. That was just when Julia 1.0 was released. So we were finally, well, we felt secure enough that we could actually tell to our colleagues that we're using this language and it would be stable for the foreseeable future. And I think the major milestone came in 2020, where we had this hydrology numerical model, hydrological model. And back then that was written in Python. And to have it fast, it was using PC Raster, a C++ program, from Utrecht University here in the Netherlands as its backend. And that was too slow, and we couldn't really change anything about it because it was PC Raster in the backend. So we started porting that to Julia. That became way more interactive, and we could control and develop it better, and it became faster. So now wflow, you can find wflow.gl on GitHub in open source. And basically from that experience, we decided to do that more often. Oh, that's nice ringtone. Back in 21, I started my PhD research, and basically I did my scripts also in Julia, still now. Like, oh, we can open windows. Yeah, it's getting hot, right?
Yeah.
We have a window open for the phone as well. Thank you. Anyway, the windows are open. I don't think there are actually more windows than that. So let's hope it cools down a bit. Yeah, there's airco, but I'm not sure if it's on.
No, it's not on. It's not open. It was on yesterday.
Guy completed the back. I think there is a control panel over there. Ah. See what we can solve when we work together? Oh, I love it. Okay. Anyway, I started PhD research. But if I'm not doing my PhD research, I'm actually working on Ribbesim, which is a water balance model for the Netherlands. We're actually creating the Dutch national water model. And this was originally Fortran code back from probably the 80s. We decided we cannot really maintain that anymore, and also not really port directly because we want to do other things. And I'm currently now working on that model to rewrite it from scratch in Julia. And the picture on the right-hand side is actually something of a week ago where we first merged all the individual water boards models. And this is a 50,000 node water balance model that's actually simulating nicely the water balance of the Netherlands. And you can clearly see the Meuse and the Rhine coming in, big rivers. But you can also see all the small individual streams and channels that the water boards are responsible for. And it's working. And it's relatively fast. We should still optimize it further. But I think the take-home message is here is that we're writing numerical models. We're happy about the speed they have. And we're confident enough to write new numerical models in Julia. And they're being used for quite serious production work. I think the Dutch water model will be sort of the largest water model you can have in the world in terms of schematizations, just because the Dutch are so crazy about water. There's basically water everywhere, so a lot of management. And if this works, yeah, you can apply it everywhere. We're not the only ones using Julia in production. I think there's a climate modeling alliance that's Caltech, MIT, GPL from NASA, and they're creating new. Let me animate this. They're creating a new ocean model numerically. There's Speedy Weather, which is used for teaching a climate model. That's also a translation of an original Fortran model. There's a complete SciML ecosystem. Most notably differential equations.gl, which is basically, it's all solvers written in Julia. I think they basically have all the solvers ever written, either as plugins from Fortran or other languages. And new research is being done on new solvers. So that's basically differentiable programming. And a lot of machine learning in there as well. Let me restart this. And another scientist at NASA is actually using the geospatial stack of Julia to visualize glacier loss or growth, if you're lucky enough. And this is basically interactive exploring a data set of a few terabytes in size. to actually see what's happening, which might be very hard to do in other languages. So let me conclude this part of the session. The good of Julia, I think, is all of the things I've discussed, of course. That's just very much built in. That's very easy to use. It works for numerical models in production, and I think larger research project at scale. Oh yeah, and I just encountered a tweet based on a research paper which compared basically AI generation of programming languages, and apparently Julia is easier to generate correct results for than Python or R. Whether you should use that as an argument for using Julia, I don't know, but still interesting. So the bad, I think, about Julia, we should be honest about this, it's still a very young language. You will notice that. I mean, Python probably has 100 times more developers in terms of ecosystem, maybe even packages, than Julia.
What do you notice it most? Or what are the most frustrating things with young?
Oh, that's the ugly. I will come to that. No, it's a small ecosystem, right? So if you have a specific niche that you're researching in, especially if you do a PhD, essentially, there will be no package doing that. You'll be the first to do that. Luckily, writing new packages in Julia is really easy. It's a trade-off, right? So if you're at the start of a project, it's fine. Back in 2014, right, when the first introduced Julia, and then there was no geospatial stack. We basically had to develop that from scratch. That's terrible in terms of hours that you need to invest to link to GDAL and get everything working. Now it's actually, I think, pretty okay for my purposes. But again, it's quite possible that you miss your package that you're interested in, and there might be bugs in interaction with other packages. I'll come to that later. It's quite specific to Julia. What I think the ugly things is, sometimes if you have an error, if you want to make Julia fast, you'll make things very type specific. Come back to that, what it means. But sometimes that means if you hit an error, you get a very long error message. It's like Java. Who noticed Java stack traces? Who knows that? Of course, Daniel knows. I remember mostly from Java, even just running code, sometimes when you get an error, it was just scrolling away. And then after a minute, okay, now you have to search for the actual error message, right? Julia sometimes is like that, especially if you use the SignML ecosystem. If you use your own package, you won't notice that. And there's no static compilation. What it means, you cannot create small binaries. So if you use Fortran or C, you can compile it, and you have like a few kilobytes and executable, and you can run it. Julia doesn't have that yet. If you can make binaries, you can make libraries, but there will be like 500 MB because it includes the Julia interpreter. So that's if you care about size, that's a drawback. But we're working on that. I think the new Julia, it's now a release candidate, Julia 1.12. It has support for static compilation, but that then has to propagate through the ecosystem. So maybe in a year, parts of the ecosystem can be statically compiled. And then you really have the benefit of both worlds. And this is for yourself to decide. Originally, when Julia was created, Python was really small and young and had its drawbacks. So I think Julia was envisioned as a Python replacement. But then before Julia got mature, Python really took off. And it's a generic language. So I don't think that Julia will ever overtake Python or another language like that. So it will be a niche language for technical computing. If you're doing geospatial work or any engineering work, that's fine. But it will be likely that some people will never know what Julia is, right? They say, oh, I know Python. And anyway, I think that concludes this part of the presentation. Questions thus far? 40 minutes in. Could you guys follow along with the VS Code? Did it work out? Or the Julia replicator? I mean, we're only going to get further into the language, right? So if it breaks down here, we won't get further.
Can we use some Docker container or run Julia? Is it possible?
Well, of course it's possible. I mean, the Docker container is probably some Linux system, and Julia runs fine on that. And the question is more, why would you want that, right? So Julia, especially with Julia up, it's so easily installable, and the environment manager is really good. So I don't need to use Docker for isolation purposes or anything. And also on the clusters, it's just installed system-wide, even for all users, and they have their own environments in their user home directories.
But you need to match all the dependencies. So, for example, if you have some cutting-edge package, you could have some Docker container to easily extend, exchange the environment. I mean, like, what do you struggle if you just have this?
I wouldn't use Docker for that. I would just switch environment from within Julia itself, because it's good like that. I have seen when I collaborate with Python and R users that the R user knows how to run R, and that's on his system. And for running Python and Docker, he has a Python and Julia, he has a Docker installation that he can easily access. But I'd say no need. And maybe also we are too advanced for most people, I think, to run Docker. Although one lecturer required to have Docker installed, I think. Well, who is Docker installed? Yeah, of course. Okay, next question.
Also trying to solve this two-language problem, like wrapping everything together into one box.
Yeah, I think so. For example, imagine that you have OS and you don't have, for example, the latest version of GLOB, and you want to use a package that uses a GLOB binary, like compiled, that is not, for example, like matching with the package that you were installing, right? So that's what, because of course, Julia also will have some OS dependencies, so you need to also manage that. The package manager will not install GLOB for you, right?
It will.
It's like Honda.
Yeah. I'll get to that. I was actually sort of disappointed by R, because if I installed it on Mac yesterday evening, it tried to compile everything, and of course that fails completely. So just going back from Julia to other languages and then trying to install something like C dependencies, I fixed it eventually. If you get the binary dependencies right in R, it also works out of the box. Okay. Let's move on. I think I shared this in the Mattermost channel. So this is my GitHub handle, and this is the OGH 2025 repository. And there are notebooks in here, Jupyter notebooks, that I will be running interactively and going through them one by one. And you can run Jupyter notebooks from VS Code just by opening them. VS Code will handle that. I sometimes like to just use Jupyter Lab to actually run the notebooks, like you may be used to. Always use Jupyter Lab or Jupyter Notebooks in general? Yeah, I have. Okay, pretty good.
So Jupyter Notebook is both for Python and for Julia.
Aha, yes. I actually made it bold. Jupyter stands for Julia, Python, and R.
Really?
Yeah, fancy. I also didn't know that. I was actually surprised when I learned that. So yeah, it works fully like that. So you can download the repository, yeah, or git clone if you're familiar with Git. And then there are all the Python notebooks and the small data sets, a raster image and a vector data set that we'll use here. So then you can follow along. You can also download it later and check it out. Yeah. I think I killed everything that I had running, so. So with the command I just shown, using iJulia and then Jupyter Lab in Julia, it will actually start a Jupyter Lab session. Might be easier to just open the notebook from VS Code, and then it will hopefully find the kernel. Depending on your system, getting Jupyter to work correctly is not always straightforward. So it's something that we could discuss in the break if you want, with a coffee, and then we can debug the system a bit. Yeah, so you know that Jupyter detected Julia if you have Jupyter kernels available, basically as a notebook choice. If you don't see this, let's talk in the break. So code, OpenGeoHub. So let's start with the intro notebook. There's a lot of stuff that I already talked about, so I will skip that. I will try to make it bigger for you. Presentation mode? Sort of. So maybe this is actually too deep of a start, but let's try it. Let's try it. So this code you already should recognize from the small demo. We can write a power function, and we don't need to define anything here in terms of types, right? We just have a and b, and we say a to the power b. So a and b can be anything. So you can write Julia code like this, and well, let's actually do that. And then we can say power 1. So that works. Oh, I lost my function. OK, that doesn't matter. Julia has remembered that. So you'll notice here that I haven't specified any types, right? So 1 is probably an integer, if you're familiar with that from computer science. But Julia has basically figured that out and compiled a specific version of power for integers. And that's basically called just-in-time compilation. And Julia can often guess what you're doing and get it fast. You can also write a manual version of this by actually creating a second power function. And then you specify specific types for each argument. So you say integer here. We can say hello integers by saying add info. So then we can basically print that statement. And then we still do the same power up command. We can execute that. I already showed you the help function. But still, let's do that. And you will see now that Julia has detected there are 2 versions of power, one generic one and the other one that I just executed. The reason I'm using Jupyter Notebooks, by the way, is that question mark works in Jupyter Notebooks. And if you do this in VS Code in the Jupyter Notebook mode, it doesn't recognize the question mark. So it's stupid VS Code like that. But this concept about power, so we can actually test this, right? We had power with 2 integers. And now it actually, this is the code paths it takes. It takes 1 integers. If we make that just one of them a float, it hits the other function. And it doesn't take the integer path. And this is a key concept in Julia that can make things really, really fast. And also really extensible, customizable, because you can basically define your own types, your own custom structs that you might have for either a raster or a specific sparse raster or your own operation, and write methods like these. For example, we can make a my measurement struct. I think this is from the base documentation of Julia, these kinds of examples. And it means we can have a value, and we can keep track of its error of that measurement, let's say. So we can make a struct. This is like an object that you also have in Python, a class. And then you can define the multiply operator in Julia for your object. And then you can actually say, if I multiply my object with any other number in the ecosystem, I have my own specific implementation of that. So you're right, my measurement is actually the value times that other number, but I also multiply my error by that other number. And if you then execute that, you actually see, so you execute my measurement, you initialize that with certain values, you multiply it by 2, and you get my measurement back. That's now suddenly 2, and it also has a larger error range. And the whole ecosystem can be defined in functions like these. You can overwrite base Julia functions. Don't do that. You will probably crash Julia. You can really,
So it's not nice to override the star operator.
for your own object, it is. But I could theoretically now override the star operator for any number in the ecosystem. And then you basically, you change the game, right? The whole Julia program language will change essentially because you redefine the core operator. That will definitely kill Julia. I'm not going to demo this. That's basically called type piracy. You're pirating on things that you don't own. But that's pretty deep for Julia. But this is also very, very powerful, right? So you can kill Julia with it. Don't do that. But it also means that this my measurement struct that I just defined, it will work with a machine learning package from someone else that never has heard of your object that you just defined. Because you just define basically an interface how it should operate with other packages. And that's it. So if you call methods star, it will create a long list because it basically gives you all the methods defined for the star operator in Julia. And there are basically 222 methods defining that. So that's for complex numbers, big ints, bit matrices, missing, big floats, unions. There's linear algebra in there, right? I'm not going to through it. It's way too much. But this is how Julia is fast because it has very specific paths for specific types. So it can take shortcuts if needed. And it's also how you interact with the whole ecosystem at large.
When you use the star, it goes through the whole list to see which is the best.
Yes. And that's a really optimized code path that compiles down. So it can create really, really fast code paths for this. In contrast to, for example, to Python, where basically if you execute Python code, it basically has not compiled that. It will check on runtime what the type is, because it basically stores the type next to it, and then start searching basically a list like this to see how it needs to execute. And this is compiled away. And that makes Julia basically fast. This might already be complex for many of you. I just want to showcase it. It can be really, really powerful. Any questions about that?
Julia, exactly that. Sometimes you can type cross it, but it's not necessary, right? You can also write functions without types.
Yeah.
It's a bit in between them.
So I think if you want to, if you go back to the first function we defined, oh yeah, I deleted that one, right? So it was this function. I think if you're prototyping, you really want it like this. And this will actually be fast, because it will just, Julia is smart enough that it reads this, and it can basically infer that if you put in 2 integers, the answer will also be an integer, or stuff like that. If you're hacking away, that might not always be the case, and Julia can get confused, and the code will be slow. And then just to make it fast, you might need either an annotation like this. You might need to allocate some space for the end result if you're working with big matrices or other things. But then you're still writing Julia code to make it fast. And those are often small, subtle touches. Any other questions? Am I going too fast for you guys? Okay.
From 0 or 1.
Yeah. I have that in another notebook with notable differences with other languages. But I believe like MATLAB, Fortran, and R, it's a one-based language. unlike C and Python, which are zero-based. So we start counting at 1. And of course, this is a really dividing feature, right? So some people are like, yeah, 1-based. It's the most logical thing there is. And then for some other use cases, it's terrible. And you need to write constant offsets. So yeah, it was a choice. And there's only, yeah, you have one language like this. There's actually hacks. No, there's actually just packages, supported packages that use zero-based indexing or even offset indexing, so you can do weird things. But they tend to introduce bugs. Anyway, moving on then. Oh yeah, this whole list. Ugh. So a little bit about interoperability. It's easy to interface with C libraries. So if you also compile your C++ library with the C interface, you can call it that. So that's actually C call called the clock symbol that's basically already loaded in Julia at start. You define that you get an integer back, and that's it. So this is actually this is a timestamp that represents time. Of course, this is calling C, but you also have packages like pycall, so you can execute Python code. There's actually Python plot, which executes Python plotting code, so you can basically use the matplotlib backend from Python for plotting your Julia data. There's rcall, so you can call rcode, and there's also, by the way, reverse one. So I think from R you can also call Python. So there's loads of interoperabilities, because I can imagine you all have your favorite packages, or you're actually maybe your quite unique package in your own ecosystem that you still want to use and call. And you can do that. And like I will show you later on with geospatial stuff, we have, of course, interfaced with GDAL, GEOS, and Proch, and all the famous packages to make the geospatial ecosystem work. So it's not that you're suddenly locked in some Julia ecosystem and you cannot get out.
We experience some kind of problem like of performance when you load libraries that are like on Python and R compared to things that are implemented directly.
I haven't benchmarked that. And so I would expect just yes, because calling another language, it's another function call, it's always overhead. So I expect some overhead. That being said, R and Python are inherently already a bit slow. Don't want to offend anyone. But so you might not notice that, actually.
It's okay. I use Proch, for instance, calling it from Julia, and the overhead is there, but it's not that annoying. It's okay.
Yeah. I think the biggest performance gains you can have is basically by passing whole arrays and vectors and not doing one number at a time. But that's a given for any language. Okay. Well, Unicode. I showed you the pi command before, but you can of course use the square root sign. But if you want to go nuts, you can use emojis, because emojis are valid Unicode, right? So we can execute this. And emojis are even a valid function name. So what I did here, I'll first show you the rest. So here's a square root operator. This is Unicode. So instead of typing square root, you would do that. I think it makes sense. I already shown you pi. Right, it's nice to use the Greek alphabet to basically define or run your math. But you can also use emojis. So what I did here is basically, this is just a function name, right? So this would be foo. So this would be the function foo that takes no arguments. Hence, there's nothing in between these brackets. So if you call foo below, foo, oh, it will give you a random number between 1 and 6 back, right? But you can replace foo by this dice emoji, and that will work as well. So I don't see a valid use case where you need a dice emoji as your function name. So I don't advise this. But who knows? Depending on your package, you might. I mean, you can just. There are games that you can play for making the most unreadable code or the fastest code or the most complex program in the least amount of lines. You could basically have emojis all the way and still execute some code base. Anyway, have fun with it. Don't overuse it like anything. Okay, moving on. I might actually skip this, given I have half an hour to go, right? Oh yeah, this is going to be problematic. So what I want to say is loops, just making a for loop. This is the for loop syntax for something in a range, do some operation. And from Python, you might have learned you don't want to do for loops over a huge NumPy array or something like that. You want to have a vectorized notation. For Julia, that's not really needed. You can do that. There's the second example is the vectorized notation. But writing a complete for loop out by hand is actually often just as fast, might be even faster. So that's fine. The other thing I want to show is that there's macros. So that's the stuff, the purple stuff starting with an @ sign. So if I execute this, the @info will say info. Basically, it's a logging statement. You also have debug and error and warn. And the other macro is @time. And with that, it's built in, always available. Then you can basically time your function. And it shows you the time spent, the allocations, and if possible, the amount spent on garbage collecting. Because it has garbage collection, so you don't need to free and remove memory yourself. The language does it for you. Of course, garbage collecting is always slow, so the less you allocate, the better. That's probably too much details. And you can see some more notations here. Also that you, for example, can create arrays. I put A is a list, basically. So this is a vector with 1, 2, 3. And then you get back 3-element vector in 64. So again, Julia recognizes the type and uses that. And of course, if you want to make stuff faster, you first have to see that it's slow. And then you need pointers to actually see what you need to fix. You need to profile your code. Otherwise, you don't know what to make faster or where the problem is. So Julia has very nice built-in stuff that you can use to profile code and check why things are slow. And a simple one is actually code warn type. So if you execute that, it will take the function I defined above here, this Euler-Riemann zeta function. And you get the Julia representation internally almost of this function with arguments, what's it doing, what it's going to infer about your about the stuff that you're doing. So I'm not going to go into detail here. I'm just pointing out that there are tools like this. And this is only the highest level because this is still in Julia. Right? So there are many others. You can go code types, I believe. So this is the same, but then without the warning. There's code LLVM. So Julia compiles first to basically Julia representation internally. Then it uses LLVM to actually go to machine code. Other languages also use LLVM as an intermediate compiler. But you can generate that code here. So if you're a computer scientist and really want to go in depth, here's the LLVM representation of the function we just wrote. So that's from Julia. I don't know what this says, right? Don't get me wrong. Okay, I know little bits, but I'm not a computer scientist by trade, and I don't need to go to this level. But if you really want to get bare bones performance, you go to this level and see, these are stupid instructions. Or maybe the easiest of all these performance measurements, if this is very long, it's slow. The shorter it is, the better. That's an easy one. And you can go one step further, and then I will stop. You can go to code native, and this is basically machine instructions. This is the lowest level you can go. These are really CPU instructions about addresses and executions on your CPU. All from within Julia to easily debug it if you have the know-how to do so. Moving on. Let me check what I'm gonna tell about. Yeah, are there any specific questions that you want to know about Julia right now?
I'm wondering about the raise, because if you just take an array and do +2, it doesn't work.
Yeah, because that's a bit undefined, right? What do you want to do?
You just add the number of each element in the array.
Yeah, you want to do each element. Okay, so the question is,
The other- Yes, I don't know.
well, I don't know about intuitive, otherwise you would have found it, right?
Yeah.
But being very honest here. So the question was this, I believe, right? So if you execute this, you will get an error. And it's basically saying, it's actually, the answer is in there. It says, I cannot take a vector and add a single number. I don't know what to do. What do you mean exactly? So you were looking for element-wise addition, right? You want to add 2 to each number in this vector. And it actually says so here, the second line, for element-wise addition, use broadcasting with the dot syntax. And then you say, so that's this syntax. With the dot, you say, do this element-wise. And then you get your answer back.
But if you multiply, it doesn't make it.
Well, then you get into linear algebra, right? Then you get stuff like matrix multiplication. So you need to be, it's something we need to learn.
It is built in.
Yeah, this is maybe actually not that intuitive. I think they had this in earlier versions of the language, and they decided not to break it.
Yeah, okay. But it's not like Python where you need to package to do it, so it's nice.
Yes. So maybe let's go to. I'm really running out of time though. So meta programming, skipping, package manager. Okay, package manager. I have a whole package manager notebook that goes through the steps, also about creating environments and projects. But really quickly to demo, I showed you how to add a package. I think I get the question from Leandro how to actually add GDOL. So I can actually do this, add GDOL. And this will give him my internet connection. It's installed GDOL now. It already had it in the environment. That's why it doesn't say so. But GDOL is the bindings to GDOL, and the dependency of that package is gdol.gll, and that has the libraries, the shared objects, essentially. And if you don't believe me that it actually pulled this in, we can run the test suite of a package from the package manager. So we can also say test GDOL. And then we're running the test of the GDOL bindings. And you can see it has the gdol.gol with a specific version number. Run some few more packages. And then it's running tests. And you can see it using GDOL 3.1, 3.11, eigenview. It finds a lot of GDOL drivers and OGR drivers, so it's actually quite a complete installation. And all tests passed. So if you write packages in Julia, there's built-in testing. There's a built-in way of testing your packages, writing tests. And because it's built in, I can actually run the tests for a package that I don't know or own. I've just said test GDOL without even inspecting where that code lives or anything. So this is very useful to actually make sure that stuff works.
And it does not work if you don't have the right dependency or something on other packages, or when would it fail?
This should just not fail, in my opinion. Of course, it sometimes does fail. And when that it happens because, for example, GDOL might do a breaking change in something, right? It has to do with version numbering and breaking changes. So if GDOL makes a change that other people didn't anticipate and depend on, it could break. But generally, it doesn't. And of course, we test all these things. We do downstream testing. But yeah, so sometimes breaks, but often it should just work. And this is, I think, the most frictionless way of actually installing GDOL in other languages and binary stuff like that. Okay, there are exercises here that you can run yourself. Since I have like 17 minutes left, I'm gonna move to, no, I'm gonna show you what there is, and then I'm gonna move to geospatial. So I have a notebook here, package manager.png, that basically discusses the package manager more in depth. And I think it's good to go through. It has the examples about adding and testing GDOM, but also how you can develop a package. And in the introduction, there's also stuff about environment management, because you can activate multiple virtual environments, just like you would have in R or Python. And they record the exact versions of your packages. So if I give that manifest, as you would call it, to someone else, they can reinstantiate that whole environment with the specific versions. So that's all fantastic. Please check it out. There's a notebook about parallel computing, because you can do parallel processing and threading from within Julia, all built in, no external packages needed, including race conditions. So of course, if you're working with threads, you need to know what you're doing. There is I think the last notebook that I haven't discussed, there's one with noteworthy differences. So if you're used to Python or R, not everything is logical, or you can find the correct function. So there's a documentation page from the documentation page of Julia itself that you can go to with these differences. It's actually quite long, the documentation, and it gives you examples for all languages. And of course, if you have specific needs for creating vectors, here's a cheat sheet for MATLAB, Python, and then Julia. So I think your element-wise addition would be in there. Maybe I should make this bigger, but I think it shows you nicely that MATLAB is quite straightforward if you want to do maths, and Python really, really isn't, right, in terms of notation. Anyway. Okay, then I'm moving to the geospatial notebook. And this is basically also the packages I've asked you to install in Mattermost. So we're using, well, a few packages. I think easy to explain geodata frames is like GeoPandas in Python. And then we have rasters, and rasters is like Rasta.io or Xarray in Python. And I'm sorry, I don't know the exact packages from R. And there's geometry ops, which is like a native libgeos, but we also use libgeos for other operations. And packages called Maki, they're used for plotting. So if you go to this notebook and you execute it, we say using raster. So that's how you use a package. You basically load it and precompile it when possible. And we open a data srtm.tiff file on disk. I provided it with the repository. And it's just a very, very small sample of the SRTM global elevation model. As you can see, it's only 465 by 457 pixels. And it actually prints pretty nicely what's in here. It says it's a raster. It has a certain type of data. It has dimensions, right? It has certain axes, as you might know them. It has a bit of metadata. It has an extent and a CRS. And it gives you a slight preview of this data set. And these are unsigned integers, and this is the notation to actually have that. But it also shows you the latitudes and longitudes already. Of course, unless you're, I don't know, Neo from the Matrix, you cannot really read these unsigned integers. So let's also plot it. And if you've loaded Maki or any, I think Daniel will be using GeoMaki, but a Maki package, you can just call plot on that raster. Of course, first time running plots can be slow. Very slow. Oh. And we get a nice visualization of this. Well, who knows where this is? What? No, it's not. No. I mean, this is completely impossible for you guys to guess, but I'm cheating now. No, you should have seen for this coordinates. This is definitely not the Netherlands, but anyway. These would be latitudes, so degrees. Anyway, this is how you plot. You can work with these dimensions. So you can call lookup on that raster and get the x dimension. And you will see this is going from -113 with a step size of, that's 1/3 of a degree probably, or to the end of the range. You can subset a raster like this with a notation using x, the start, then a range to the end. So this is specific to rasters and dimensional data. And you can also see that this is nice. I timed this function, and it says, well, apart from giving the time, it also says it spent 99% of the time compiling this function, because this is the first time we called this. This is the first time we called view, raster, and these other things. So as soon as you call this again, it's gone now. Where's it gone? Ah, here. It actually is now a single allocation, and it's, well, 100 times as fast. So this is the just-in-time compilation that Julia does and needs to do once, and then it knows what to do. And you can see we've now subsetted this raster, right? It becomes smaller, extents have changed. And the nice thing about most Julia objects, this is wrapped as a raster, right? There's a lot of metadata, a lot of info, just like you might be used to from R. But underneath, this is just native Julia stuff. So it also behaves as a native Julia thing. So we can rewrite this to float 32. We can multiply that by a number. We can then clamp it between 100 and 200. All built-in math operations. And that would just work. And you actually get a raster object back. But now you see it's all 200s. And I think this is one of the, I've showed you before about types and that you can then interact with the whole ecosystem. This is how these objects can behave to the whole ecosystem. This is just a matrix, essentially, of data. It behaves as a matrix. And all packages that have operations or define operations on a matrix can work with a raster now. And that's really, really powerful. And it can also produce really weird bugs, but it's a downside. And then, importantly, we can write this subsetted raster to disk. So we just call write. We give the file name, and then the variable that we named it. I have to say force is true here because I've called this repeatedly. So this overwrites the file on disk. And that's it. That's how you basically operate with rasters. There is, of course, a documentation page that I also linked in this notebook that goes way more into depth. It has a manual about all the functions. It has zonal statistics. You can warp it, trim it, crop it, all kinds of things. Definitely check that out. And this can also open netcdfs, right? It can do multidimensional things. And interfaces like that will be also shown by Daniel, I believe, after the break.
That's basically rasters if your tile fits into memory. And there's the equivalent of X array in Julia called gaps arrays. And this allows you to put your chunks on disk, working with really big arrays. And then you also need to load into memory the current chunk you are looking at.
I believe rasters can even also do that, but I'm not going to go into package details, but I'm looking forward to it. That was raster data. So sorry, I lost my tabs. Yes. With 9 minutes to go, I will do vector data. Any questions thus far? Sorry, yeah, it's hard to learn a language like in an hour and a half, right? And I just have to tease you a bit. You can also make rasters from scratch. I'm going to skip that. But basically, this is to demonstrate that you can really start with a matrix, create that without knowing anything about rasters, defining basically your axis from scratch, and you can create a new raster object from it. So you can really build stuff and then plot it again. So now moving on to vector data. I'd say from history, we really have seen raster data and vector data as separate things, and you often have separate packages handling them. We still have that in Julia. I think also for some data handling, especially if you use GDAL behind the scenes, you're sort of forced to do that. But it's also easier to, well, maybe we shouldn't see them as completely separate, right? A raster is just a very structured mesh or a very structured point collection. So you should be able to switch between them. Personal pet peeve of mine. Moving on, we have geodata frames. So this is also installed. And just like rasters, we can read a data set. It's called Zion.geopackage, which defines the borders of Zion National Park in the US, which is also where the SRTM dataset was. And if you load that, you get a data frame back. This is just like you are used to pandas and probably Tibble or something. I'm not sure in R. And you'll see this data frame. It only has a single row. It has a geometry, and then loads of attributes that you can, well, metadata. And since this is a data frame, you can go to the data frames documentation, just like you would go to the pandas documentation and do all kinds of things. So geospatial data frames are really just data frames. They're not special. So have fun playing with them. We can plot these things again. So if we call df.geometry, we have the geometry column, and we can plot that, and we see the park outline is a bit weird. I don't know. It's not a straightforward square. We can buffer this, so we can, oh, this jumps very weirdly. We can use libgeos, so this uses geos in the back, and geometry ops. And then we can buffer this whole geometry, I would say 10,000 meters, because at this scale, one you wouldn't see. And then we have something unrecognizable, a nice blob. So this is in UTM. And we can check that with checking the data frame of the metadata of the data frame, or more directly using Geo interface calling CRS. And then we see it's well-known text, and it's actually UTM zone 12. And that's why you can actually buffer by meters. We can reproject that to WGS84 by using geometry ops reproject. We need to use proj in the backend, so we're actually using the proj C++ library to do this. And if you then, we call reproject on the whole data frame, so nothing seems to have changed. But if you then plot it, you will see that the axes have changed, right? If you check the other plot, this is all in the hundreds of thousands of meters, and this is in degrees. And we can also write this to file, geodata frames write, with the specific option to GDAL to override the file. And let's make it GeoJSON. So we just give the extension with it, and it knows what to do, and it will write in GeoJSON. We can check that it actually did that by reading that file again. And then we can see it's, with a lot of enters, it's actually a JSON. 5 minutes. Well, just the last thing that I want to show you then, you can, of course, combine all of this. We can have from rasters, we have the raster, we have the geometry from geodata frames. And we can, for example, mask the raster with this geometry. And if you call that, you get a raster back. And now you will suddenly see that most of this raster is missing, which is the value in Julia to indicate that there's no data there. So you don't need to play around with -999 or other real values to indicate that something is invalid. We can use missing. And if we use that to plot, we can see we have nicely cut out the elevation from the SRTM model for Zion National Park. I will leave it at that. The rest is up to you to actually execute and run. I put many more links to documentation pages in here. And I also like to shout out to Anshul Singhvi, because he has written a lot about Julia Spatial and has helped writing half of this at least. Because we're writing a book together, Geocomputation with Julia, following geocomputation with R and geocomputation with Python. So this follows in that series. I've put a link here. I've got to admit, it's very much a work in progress. So I think half of the chapters are not yet there, but please check in a month or two, and maybe half a year. And then I hope to have all these examples that I've now given you nicely in a book. And then it's as easy to read as the Python and R versions. And we really like to keep the examples the same. So you can really have them side by side and see how the languages compare. And they shouldn't differ much at all. In 2 weeks, I'm actually going to a conference, Spatial Data Across Languages. This was initiated by Edzer Cabesma. And you should have seen him because he's a professor and I was here the first 3 days. And he initialized this conference, or more of a workshop, to make sure we're doing the same things in the same way, spatially, in terms of all these 3 languages, in Python, R, and Julia. So we can learn from one another. That's the idea. And yeah, this concludes the session with 2 minutes to go. So any questions?